Hello, everyone. Any questions about last session? So there is a question. After we find the optimal ArchITECture in AutoML, do we retrain that model using new training data? That depends. You are going to retrain definitely one final time. It could be on the same type of data that you were using to do your AutoML. For instance, if you were using CFAR10, then you were using the validation portion of that data set to come up with your model. But then you do one final round of training, because when you're doing AutoML, you don't fully train. You train for a couple of epochs to just get a sense of the accuracy of your model. So one final round, you're going to train it on CFAR10 training data, and then you're going to put it in production, test it. If you're doing transfer learning, then you're going to change your architecture a little bit. Maybe you want to take your AutoML architecture and make it deeper because you want to apply it on ImageNet. Then you're going to do one final round of training on ImageNet and report your results on the test data. Does that answer your question? Okay, perfect. And the question is, can we also implement dropout in AutoML? Yes. So one of your decisions could be, should I put a dropout or should I not put a dropout for one of your layers, especially the last ones? This could be one of the decisions coming out of your controller, RNN. In this case, maybe it could be one of your mutations, which should be fine. I'm not sure if the paper is doing that, but it is doable. Does that answer your question?
If the decision for the dropout is a yes, then the architecture is again trained based on the dropout, the selected architecture, right?
Yes, exactly.
Okay.
So if you decide to put a dropout in the end, then you're going to do a training on that using dropout.
Okay, got it. Thanks.
Yeah, sure. Any other questions? Okay, perfect. So last session, we started with AutoML, neural architecture search, and we had two options to do the search. One was using reinforcement learning. The other one was using evolutionary algorithms. But this idea of evolution is not new. Actually, people from 2000 and 2001, they were trying to use that idea, and they were calling it neuroevolution of augmenting topologies, NEAT, but they were doing it for fully connected networks. So all they had was a bunch of neurons and a bunch of connections between neurons. So the idea is not new for using evolving evolutionary algorithms. I don't want to go into more details of, or a lot of details of evolutionary algorithms, because this course is about deep learning. But what I want to focus on is how do you actually formulate the problem of AutoML so that you can use these sorts of algorithms. Let's see. You can have a population of chromosomes, and these ideas are from around 2000. You can have a population of chromosomes. In our case, it's going to be a graph. And each graph is going to have a bunch of nodes. It's going to have a bunch of edges. And then you're going to start with a very simple graph. So it's going to be a very simple neural network initially with minimal complexity. So that's what you're going to start with. And then you're going to keep evolving it over time, over generations. What are you going to do? Initially, your architecture was very simple. So you're going to keep adding neurons and keep adding edges, weights to your graph. And then this is going to happen through mutation. And mutation is something that is random. You sometimes add a neuron, a new neuron, and sometimes you add a new edge. And sometimes it's going to lead to better performance. Sometimes it's going to lead to worse performance. And then there is going to be a crossover stage. So think of crossover as reproduction, the way that a two human beings reproduce. Here you're going to have two graphs reproducing new graphs, new children. And then you're going to look at the historical markings, like what was the performance of this graph, the other graph, what are the edges, what are the nodes, and then decide how do you want to combine the two. So now after this stage, you're going to have some offsprings, some children. But then you're not done. You're going to divide your graphs or your chromosomes into species. And these are subpopulations. And this is based on some similarity metric. Okay? You're going to say that according to my chosen similarity metric, these set of graphs belong to the same cluster. The other ones are going to belong to the other cluster. And that's going to give you your species. And then your species are going to do the crossover in the next generation. Now, each species is gonna grow proportionally to its fitness. But what is fitness? Fitness is exactly your performance metric. In terms of classification, that's going to be your accuracy. And then each species is going to evolve separately. And then you go ahead and do these iterations over and over again. From 2 up until 5 is going to get repeated. And then in the end, you're going to end up with a neural network. It's going to have 1 layer deep. So it's not going to be too deep. And it's going to be fully connected, or actually connected according to the edges that you evolved. And that's going to give you a neural network. Any questions about this? So this is around 2000. People are using evolutionary algorithms to evolve neural networks, but they are not deep. They are shallow. They have only 1 layer. So yeah, crossover, as I mentioned, I don't want to go into a lot of details of how the evolution is going to happen, but from the big picture perspective, think of it as the reproduction way. So 2 graphs are going to combine together and give you the children, okay? And then the way that they're going to line up is how similar they are. How can you actually put 2 graphs on top of each other in terms of their nodes and edges? So yes, they cross over and then mutate. That's correct. And how many times do we loop through 2 and 5? A lot of times. So this evolution is going to happen over a lot of iterations. Does that answer your question? Okay, perfect. But now we want to make things deeper. We don't like shallow networks, but to make things deeper, we need to rethink what is going to be our chromosomes, what is going to be our graph, what are going to be our neurons, edges, nodes, etc. in the graph. And that's the idea of DeepNEAT. And it's this paper. Your nodes are going to end up being your layers. So hidden layer 1, hidden layer 2, hidden layer 3. So this is now, each layer is a bunch of neurons. So now you're changing your nodes to be layers. You're changing your edges to be connections between layers. And that's going to be the way that you're going to do. You're going to go deeper. So that's the big picture. So the idea is, how do you create your graph? This is the way that you're going to create your graph. Your layers are going to be the nodes of the graph. The connections are going to be the edges. And then from one layer to the next one, for instance, you can do convolution. But this is not enough. What is going to be helpful is a way to combine these two together. Evolve both the macro structure. So this is going to give you the macro structure of your neural network. This is going to give you the microstructure of your neural network. So now you want to combine the two. And that's the idea of co-evolving the depth and the modules that you're going to go put from one layer to the next layer. And that's the idea of CoDeepNEAT. What you're going to do, you're going to have 2 populations. One population is for your modules. One population is for your blueprints, the big picture, the macro structure. The other one is the microstructure. And then you're going to evolve them together simultaneously. So what is a blueprint? This is a blueprint. This is what we have been doing when we were designing our neural networks. We were saying that you have some input image, you do some operations on it, a block of operations, and then you do another block of operations. You have the option to repeat some of your blocks, and then you're going to output maybe some class. So that's the big picture, the blueprints. The modules are going to focus on, for instance, number 1, and then try to evolve it. For instance, should I use convolution? What should be the depth of my convolutions? Sorry, what should be the number of channels or the number of filters of my convolution? What should I use 3 by 3, 5 by 5? And these are all the mutations that can happen. And they're going to happen at random. And some of them we're going to keep, some of them we're going to discard. And then in the end, once you learn your blueprint, once you learn your modules, you can combine them. You can assemble everything together. You can take that module, put it here and here, and then there's another module that you're going to put for number 2. And there are also some other decisions that you can make. For instance, what should be the number of filters? What should be the dropout rate? Should I do weight scaling? If yes, how much? Weight scaling is when you're doing L2 regularization. What should be the kernel sizes? Should I do max pooling? Yes or no? These are the node hyperparameters. These are the hyperparameters of here. And then you have also some global hyperparameters. What should be my learning rate? What should be the momentum in the stochastic gradient descent? What kind of data augmentation are you doing? For instance, hue shift, saturation. Should I crop the image? How much? Or how big should that crop be? Should we do spatial scaling of the image? So these are all data augmentation. Should we do horizontal flipping? Yes or no? Should we normalize the data by the variance or no? Should we use Nesterov accelerated gradient? Yes or no? And you can have a list of other global hyperparameters. And there is a question in the chat. So blueprint is macro and module is the microstructure? Yes, exactly. So this blueprint is the macro structure of your neural network. You're going to say that I have 3 hidden layers, and then each one of those modules, you're going to also evolve. Those are the microstructure. So one of them is the blueprint is following this idea that each node in your graph is a layer. So these are layers, and each edge is a connection. The other one is looking at the microstructure. What should be the number of filters, dropout rate? Should we use convolution? Should we use separable convolutions, etc.? And there is another question. Is this method applied in a general sense across multiple data sets, or is this done per data set? So no, this is done per data set. And then the question of whether this is generalizable is another question. Okay, so far so good. Let's take a look at what type of architectures are going to come out of this. This is the blueprint that is going to come out of these operations. So you're going to say that my input is going to get fed into nodes 3 and 4. Node 4 is going to look at my input. So that's a residual connection. And the outcome of the third one is going to get fed to 4. And then you get the big picture. So you're going to start from a very simple, I don't know, maybe 1, 4, 6, 8, 2 with minimal complexity. And then you keep adding edges and nodes. Before I answer the question in the chat, I want to finish this and then I can answer it. And then as soon as you plug in those modules or those microstructures for each one of these nodes, you're going to get something, a neural network that I cannot plot it here. Maybe it's too tiny, but let's focus on some of these operations. Maybe let's focus on this operation. Let's zoom in, and that's what you have. You are going to end up with a 2-dimensional convolution. You're going to end up with 103, 34 for your filter size. Your kernel size is going to end up being 3 by 3, and then you're not doing any strides. For some other ones, you're striding. Let's focus on another one. Maybe this last operation or one of the last layers. You have a different number of layers. Your kernel size is 1 by 1. So it is deciding to use a 1 by 1 convolution. And then the stride is also 1. Okay, there is a question in the chat. Since the blueprint and the modules evolve separately, are we then assuming that the macro structure is independent of the microstructure? They are not actually being evolved independently. So they are co-evolving together. They are not independent. Okay, because it depends. For instance, you're going to have a family of module 1s, and then you're going to evolve them. So they are going hand in hand. Otherwise, you're not going to be able to know how fit your model is. What is its performance? What is the accuracy? There is another question. Is this a very labor-intensive task to make sure that all the modules and nodes have compatible dimensions, operations, etc.? Are other AutoML methods more efficient than this because of that? Actually, because of this macro structure and the micro one, you're going to be able to ensure that whatever that is coming out of your module is compatible with the next layer. So these are some constraints. So whenever you are mutating, you are not going to mutate things that are impossible. So you're not going to do explorations that have different number of outputs compared to the inputs to the next layer. So you can control all of them. Okay. But the cool thing about this process is that you're going to know how deep your model is going to be. You're going to decide, you're extremely flexible. what operations you want to choose, what is your learning rate. So you can handle all of them, but maybe it's too much. Maybe your search space is too flexible. Any other questions? Has this method come up with architectures that hadn't been used before? Of course. And that depends. What do you mean by architecture? The entire architecture is going to be unique. So no human being is going to think of such an architecture. But if you mean, are they using something totally different from convolution? The answer is no. Okay. Does that answer your question? Okay. And I'm sure at that time, they were not using attention. So no, still, we are going to see in the future that using AutoML should also be, you need to involve some human intuition as well to give you much better performance. Okay. So the reason I went through this paper is that the idea of evolution and evolving neural networks is not something that hasn't been around. It has been around since 2000 or 2001. Okay. Up until this point, for AutoML, none of these stuff you're going to be able to do at home because they are time consuming. They're going to take a lot of time and resources. Can we somehow make it manageable and get around with having only one GPU? So let's try to do that.